Hi and hello to everyone. In this video, we are going to discuss about the how to draw the spectrum and finding out the frequency component and the amplitude of an amplitude modulated signal. Okay, the signal we are taking is an amplitude modulated double sideband. It's an amplitude modulated double sideband suppressed carrier signal. Okay, so this is that signal x of t, right? You would be knowing that this is your message signal and this should be your carrier signal. Okay, so the question is we have to find the frequency component, their amplitude, and plot the double-sided spectrum. Okay, so your x of t is 100 cos 2 pi 10 power 4t cos 2 pi 10 power 7t. Okay, so the carrier's amplitude depends on the message signal. Okay, so this is the message. This is the, I can simply say this is the message signal. And this is the carrier, right? So carrier signal's amplitude depends on the message signal, right? Okay, so how to proceed? We know that cos A cos B can be written by this trigonometric expression cos A plus B plus cos A minus B divided by 2. Based on that we are writing this. Okay, then what I have done is this is cos A plus B, this is cos A minus B. Okay, so cos A minus B, we know that I can 10 power cos of 2 pi 10 power 4 minus 10 power 7, we will get the answer in negative. Cos of inside the braces we will be having the negative term. So here the cos of 10 power 7 minus 10 power 4 both are equal because cos of minus theta is cos theta. Okay, right? Now what we are doing is we are taking this 10 power 4 2 pi f. Okay, f is here 2 pi ft, right? Here let me take this frequency as 10 power 4 plus 10 power 7 as f1, and 10 power 7 minus 10 power 4 is f2. These are the two frequencies. I am using the some constant like f1 and f2 to represent these values. Okay, now this entire thing 2 pi into multiplied with 10 power 4 plus 10 power 7 is omega 1 I am taking. 2 pi 10 power 4 minus 10 power 2 pi 10 power 4 minus 10 power 7 I am taking as omega 2. So x of t, this is my x of t, can be written in either in terms of omega or in terms of f. Okay, so your omega 1 is nothing but 2 pi f1, omega 2 is nothing but 2 pi f2. f1 value is 10 power 4 plus 10 power 7, f2 value is 10 power 7 minus 10 power 4. Okay, got it. Now this is the Fourier transform relation. What is a Fourier transform? It converts a time domain signal to the frequency domain, right? So here also we can represent the answer in the frequency domain either in the form of omega or in the form of f. This derivation and the spectrum and all I made a separate video. You please watch that. It will be helpful. Okay. Now this is the result we have. Now what we have x of t, where x of t is 50 cos omega 1t plus 50 cos omega 2t, right? So what is cos omega ct? It is pi del of omega minus omega c. So in place of we are putting 50 here, then how we can write cos omega 1? Cos omega 1t can be written as pi del of omega minus omega 1 plus pi del of omega plus omega 1. Similarly, I can write cos omega 2t as, okay, this term. That's it. Now we are multiplying 50 inside, we got the terms. Okay. Now what about the spectrum? We very well know that del, okay, we have something del t. Let me take del t. If we integrate, this is 1. Okay, provided del it exists only for t equal to 0. Similarly, if something is del of t minus, let me put ta dt. Okay, so this exists only at t equal to ta. The point here is inside the bracket of del it should be 0, then only it will be 1. Okay, if you look here, it is omega minus omega 1. So when omega is equal to omega 1, when omega is equal to omega 1, it is the magnitude is 50 pi. Okay, so this term corresponds to this frequency, right? Now come to the second term. We have 50 pi del of omega plus omega 1. So omega should be equal to minus omega 1, right? minus omega 1. So this term corresponds to this, right? Similarly, come to the third term. Inside the braces it should be 0. So omega should be equal to omega 2. Okay, when omega is equal to omega 2, what is amplitude? It is 50 pi, right? So this is this term when omega equal to omega 2. Look, come to the fourth term when omega is equal to minus omega 2. Okay, when omega is equal to minus omega 2, that is the this term, right? So this is the what I can say, this is the Fourier transform of the given double sideband suppressed carrier signal, and this is the spectrum. Okay, now we can either represent the things in the form of f also. If you are writing in the form of f, you should use this relation. You should use this relation, right? For easy understanding purpose, what I can say here is it is nearly the same. We can replace omega with f, provided if you have something called del, you divide the amplitude by 2 pi, right? So make a note here. We can interchangeably we can use omega or f, nothing wrong, but when there is delta impulse, okay, del term, we have to divide by 2 pi. Del is divided by 2 pi. Okay, keep that in mind. So if you are dividing everything by 2 pi, what happens? Pi will get cancelled. We have only 1 by 2 in the denominator. We have 2 in the denominator, right? Okay. So so based on the second, in terms of f, I can write it like this, right? When look at the first term, when f is equal to f1, this corresponds to this term. When f is equal to, look at this term, inside the braces it should be 0, right? When f is equal to minus f1, it corresponds to this term, this component. When f is equal to, your f should be equal to f2, it corresponds to this component. Here f should be equal to minus f2, corresponds to this. So this is the spectrum of what I can say, the given signal in terms of f, right? Again I am repeating what is f1 and f2. Okay, and you can also compare this thing, right? Either you can represent the Fourier transform spectrum in terms of omega or in terms of f. But remember the point, if you are having omega, just you can easily convert to f by dividing everything by 2 pi. So 50 pi divided by 2 pi, you will get 25. Okay, right? Okay. Thanks for listening.